to get our feet wet with talking about all these sorts of approximations, we should start with one that's relatively easy to work with. And in fact, we've kind of already seen it. So we're going to illustrate these techniques and the main ideas using left and right endpoint approximation. To do that, we should go back and recall that we defined integrals in terms of, or the definite integral, in terms of left and right Riemann sums. So the definite integral of f of x from a to b, so the area under the curve of this function f of x, was defined two different ways. First, it's a limit of, as n goes to infinity, of what we call the left Riemann sum. So from I equals 0 to n minus 1, we're going to add up all these f of x sub i's times delta x, where we defined delta x to be b minus a over n, and the x sub i's are all a plus I delta x, for I being 0, 1, 2, and so on. Now this is what we call the left Riemann sum. And similarly, this is exactly equal to the limit, and it's equal in the limit only, of the sum from I equals 1 to n of f of x sub I delta x. So let's break this down real quick. What actually differentiates these two things? So this being the right Riemann sum uses the right endpoints of the interval. So to clarify, right, I'm going to draw a picture here. Okay, and let's say this is our function like this. Okay, here's A, and here's B, and we partition this interval. So if we're thinking about the area under the curve, we would be talking very literally about the integral. And when we break it up into the partition points, right? So maybe this is x1. Actually, let's do fewer. I don't want to spend all the time illustrating. And they should be equally spaced apart, really. So I'm just going to call this B, just for the sake of this is going to be B. I don't want to remember that we want them to be equally spaced apart. So at each of these points, we find the function value. Okay, so this width right here is our delta x, and it's the same across, right? And if we want to find the left Riemann sum using this partition, we'd be using the left endpoints to determine the height. So those are the left endpoints, okay? And so I'm just going to illustrate here what the left Riemann sum looks like, right? So we're going to go up to this point, across, down, up to this point, across. So these are rectangles, fundamentally. Another way of thinking about this, well, actually, I'll get into that later. But so then, we're going to suppose that the area enclosed by these rectangles is our approximation. And in the limit, they should be getting really close to the integral. Now remember, this is what we did already, right? We explored this in the beginning of chapter 5. And I'm going to shade the error. So what I'm shading right now is the error and it might be positive or negative, depending on whether the rectangles are an overestimate or an underestimate. But basically, it's the pieces of the integral that don't match with the left Riemann sum here. Okay. From this, the approximation is just don't do the limit. So fix the number of subdivisions n. Then we define the left endpoint approximation as L sub n is equal to the sum from I equals 0 to n minus 1 of fx sub I delta x. And we could write that more succinctly as delta x times, or not more succinctly, but if you want to be precise, right? We start with f sub a plus f sub 1 plus dot 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 plus f sub x of x sub n minus 1. Okay, now notice we have n additions here and 1 multiplication. So it's not really computationally not that complicated. It's a really effective and, if crude, approximation. Okay, so this is the left endpoint approximation. The right endpoint approximation is defined similarly. We just use the right endpoints. So we start at I equals 1, go up to n of f of x sub I delta x. And this yields delta x times f of 1 plus f of 2 plus dot 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 plus f of b, because remember, b is that last endpoint, right? So these fundamentally are not that different, and we can relate them actually very easily. So notice that the only main pieces that are different are this and this, right? So in other words, notice that R of n, so R sub n minus L sub n, so the difference in these approximations is just f of b minus f of a times delta x. Cool, huh? Now, if we're thinking about this in terms of the definite integral, right? We kind of explored this a little bit, but it's actually really important. Like the ideas here are much deeper than you realize. If we take the absolute value of this, right? What we're really talking about is the absolute value of the difference between f of b and f of a times the absolute value of b minus a divided by n, okay? And now you can see that as the limit of n goes to infinity of the difference between these two approximations, because we're taking a limit of some constant over n, is 0. So these approximations get really close to each other as you go further out and use a smaller or a larger number of subdivisions n, okay? So let's actually see this in action, okay? So for both, so we're going to perform example. We're going to approximate the integral from 1 to 2 of dx over x squared using L sub n and R sub n, with our number of subdivisions is going to be 5, just to make it easier on us. If you're using the spreadsheet technology, you can comfortably go up to like 10, 20, 100, no problem, because it's just dragging and dropping the same formula over and over. And we'll find the error of each. And we're going to denote these. So each new method that we denote the error for, we're going to denote using the subscript is the letter corresponding to the approximation that we're using. So E sub L is the error for the left endpoint approximation, and E sub R is the error for the approximation using the right endpoints. Okay. So first of all, and this isn't, typical, or it's not guaranteed, we do know how to find the actual integral. So just for the sake of, making sure we know what the error actually ends up being, if we integrate this, we know this has a standard antiderivative, so we typically wouldn't use numerical integration for something like this. But here we are. And then if you actually calculate this, right, this actually ends up being 1/2. Okay. So how good is our estimate? We'll compare it to 1/2, right, or 0.5. So if we set n equals 5, then delta x, remember, is b minus a over n, is actually 2 minus 1 over 5. So 1 over 5, that's 0.2. Okay. All right. In order to use the left and right endpoint approximations, we need to find the function values at the endpoints. Okay, so we're going to find our x sub i's and then our f of x sub i's. Okay, so our table here, and you can, you can follow along if you want. You can skip to a point where you're not bored out of your mind, because I'm really just writing down values. I previously calculated these values, but if you wanted to do them, right, you're literally taking a, which is 1, adding delta x, which is 1.2, adding delta x again to get 1.4, all the way up until the last 0.2, and then finding the function value at those points, which is just plugging it into 1 over x squared. Okay, so 1 over 1 squared is 1. 1 over 1.2 squared is roughly 0.6944, then so on. And notice here that I'm actually rounding. These values, we can get more precision for some of these, okay? But use consistent rounding. Otherwise, you could get some error propagation, which isn't really something that we need to worry about too much in this course, if at all. There we go. Very nice. All right, so we have 6 data points. And if we're going to use the left endpoint approximation, so L sub n, or I should say L sub 5, is the sum from I equals 0 to 4 of f of x sub I times delta x. And we typically can write the delta x at the front or the back, whichever one we're comfortable with. But I'm just going to go ahead and put it at the end. So this is f of 1 plus f of 1.2 plus f of 1.4. You get the point, right? I'm just adding up all the function values, except for the last one, and then multiplying all of that sum by 0.2. Then you can verify with your calculator if you'd like. We get 0.6213, roughly, Okay, this is all approximate because we're working with decimal numbers, but multiplying by 0.2 adds that extra digit of accuracy. And so now, this is what we approximate as the integral. So what we're saying is, this is roughly I, or the integral from 1 to 2 of dx over x squared. Okay, but how good is this estimate? So then we have to find the associated error. So E sub L, in this case, is I minus L sub 5. So the actual value of the integral minus our approximation. And so 0.5 minus 0.62183, and that is negative 0.12183. Okay, what does this mean? If it's negative, that means L sub 5 is an overestimate, which we know, we can see it clearly because 0.62 whatever is greater than 0.5. That's fine. But this directly is telling us when the error is negative, then our approximation is an overestimate. Okay. Similarly, then let's do r sub 5. So remember, r sub 5 is the same idea except we use the right endpoints. So I equals 1 to 5 f of x sub I delta x. I'll spare you all the excruciating detail. But then roughly then that's going to be, well, actually exactly, that's going to be f of 1 plus f of 2. No, not f of 2, sorry. F of 1.2, sorry, plus f of 1.4 plus dot 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 plus f of 2 times 0.2. That should be higher, sorry. Okay, and that if we calculate that, we get roughly 0.43078. Makes sense, right? Okay. Then, let's find the error associated with this approximation. So I minus r sub 5 is 0.5 minus 0.43078, or roughly 0.06922, which means r sub 5 is, by virtue of it being positive, is an underestimate. And ultimately, both of these, right, deciding which one is better than the other, just take the magnitude of both of them. Notice that E sub L, or the absolute value of E sub L, I should say, is 0.12, and the absolute value of E sub R here is 0.06 or 0.07. So nearly double the error of the other one. And that means, you know, the right endpoint approximation here is much more accurate. And but they're both not that great, actually. They're not very good. We would hope that they get better as we pick a larger n, and that does end up happening. But how much better? That's a question that we still have to resolve for the other techniques. So as we move on to the next technique, which is the midpoint rule approximation, we'll talk about how it's an improvement on this